this slide, we'll examine the analysis equation of the DFT. The analysis equation is this. xk, the DFT coefficients from small k equals to 0 to n minus 1 is given by this expression. Small xn is the input vector, and it is of n elements, typically real. Actually, it can be complex as well. There's no restriction. And all we need to do is to multiply xn with this symbol here, and this symbol represents this expression. For each value of k, so let's assume that we are interested in capital X0, then we'll substitute x0 here, k as 0 here, and we will iterate over n. So you'll see that to calculate one DFT coefficient, we are going to multiply all of xn with this expression. So there will be n multiplication for one entry of xk. And we have n entry of xk, there will be n squared operation. So Fourier transform in the most basic form require n squared operation. Fast Fourier transform use n log n operation, and although we won't study it, we'll always use it in MATLAB. Now again, as we have seen in the synthesis equation, the analysis equation can be casted in matrix vector product. Let us now put xk on the left. So we have xk here, and it will be capital X0, x1 until xn minus 1. Let's examine one element of xk. So let's examine capital X bracket 0. It is this expression here, a sum of small xn multiplied by e minus j 2 pi over n kn. Let's put xn as the column vector here. So we have small x0 until small xn minus 1. How to realize this sum of this expression? In matrix vector form, it is this row that will be multiplying with this column to get the first element. So this guy is nothing but elements realized by this expression here. And you will realize that as we move along this row from left to right, we are moving along the letter n. Because this is the kth row, the kth equals to 0th row, kth equals to 1 row, k equals to 2 row. So each of these row of this matrix is representing different values of k. The columns, as we are moving from left to right, is moving along letter n. So again, the interesting and more insightful visualization is to visualize this guy. The first element is e minus j 2 pi over capital N. Now this is k. K equals to 1. So this is 1, this is k, and we are moving along n. So the first element is n equals to 0. When we substitute that, e to the power minus anything times 0 is 1. The second one is e minus j 2 pi over n. K is still 1. Small n is 1, so it's this. As we move along here, is e minus j 2 pi over n times k is 1, n is 2. So when n is 2, it looks like it's 2 times this guy. When n is 3, it's 3 times the first guy. N equals to 4, 4 times the first guy. You realize that again this is a rotating phasor. The only difference to the previous slide was that there's a minus sign here, and this minus sign, you realize is that it makes the rotating phasor rotate clockwise direction. So now you can fill up this matrix, and we call this the DFT matrix W. The elements specified by this notation over here. Let's now visualize this W matrix another way. The small little w is this expression here, e minus j 2 pi over n times that little n here, where this little n is this little n. So what happened? Well, we're interested now to visualize what happened in this row 1. Okay, so it is w0, w1, so we are moving along little n. Well, when we fill up this, we saw that it is a phasor that is rotating clockwise. So what did I do? I just convert these elements into the polar form with magnitude and with phase for different entries. And now, since all the magnitude is 1, along this row, I draw a circle with the constant radius to represent that the phasor has magnitude 1. Now I plot the phasor for different phase value across n. Remember, this is along the real axis, making 0 degrees for the first element, making pi over, in this, because capital N is 8, pi over 4 for the second element, pi over 2, and it is rotating. Can you see that it looks like the phasor is rotating clockwise, and it moves one round after n sample, and at the 8th sample it will repeat here again. What about the second row? This is row 0, row 1. This is row 2, k equals to 2. He's rotating faster. In this case, he's rotating by pi over 4. He's rotating by pi over 2, 90 degrees. As we move along, he's even rotating faster and faster. So this is the interpretation of the W matrix for analysis. Thank you.